All right. So far, we've talked about what temperature is, and then the transfer of uh, temperature somewhere else, which is heat. We've talked about phase changes. Now we're going to wrap all this up into two fundamental laws, the first law of thermodynamics and the second law of thermodynamics. We've sort of seen evidence of these two laws throughout everything we've talked about, but now we're just going to formalize them. But before we do that, we need to review absolute zero just a little bit. Um, so as you probably figured out, there is no upper limit to temperature. So that means things can just get as hot as we want them to be. You could think like the surface of the sun, or there's some stars out in the universe that's even hotter than the sun that we have in our solar system. Um, So I guess I should say, as far as we know, there is no upper limit. So this is as far as we know. There's no reason to think that there's an upper limit, at least. So if we think about going from something really cold to something really hot, that's when we talked about phase changes, um, we know that as thermal motion increases, a solid melts and then vaporizes, right? We can see this in our diagram down here. As we increase energy, a solid will melt and become a liquid. And if we keep adding energy, it will vaporize and become a gas from the liquid. If we keep going, if we increase the temperature even further, those molecules will break up into individual atoms, and then the atoms will lose their electrons. And this is actually that fourth state of matter that's very rare in everyday life. But this is a plasma. So this is very high temperatures. Um, when I worked in a plasma physics lab at App State as an undergraduate, when we trapped gaseous plasma, it had like the same temperature as the surface of the sun. So plasmas are very, very hot. Um, Clearly, given what I said earlier, we could keep going and just increasing the temperature as far as we know, as much as we'd like. Um, there is no limit over here. But there is a limit down here. There is a definite limit to how cold something can get. Um, and of course, that is absolute zero. I've mentioned it before, but we're going to talk about exactly how this was figured out. Um, so in the 1800s, various physicists doing experiments found that essentially under constant pressure, all gases they would expand or contract by a specific amount if they were heated or cooled. So you can imagine if you just have some amount of a gas in a chamber, if you increase the temperature, it's going to expand a bit. So the volume goes up. And if you cool it or decrease temperature, the volume is going to go down. We sort of know this. We've talked about it already. But it turns out that there's a bit of a relationship here. So the volume of this gas would change by, your volume would change, let's see, the change in your volume would be about 1 over 273. And I'm not going to say equals. I'm going to say is proportional to. So there's this constant. So if you add plus 1 degree Celsius, the volume would change by roughly this much. So you sort of get a linear relationship. Okay. Now, obviously, they couldn't actually bring anything down to absolute zero in the 1800s. So what they had to do is they had to extrapolate. And you all have done something similar to this before, I believe in previous labs. So they did some experiments here, right? And they collected some data. So then what they could do is they could fit a line to it, just like you've been doing in lab. And then they could look along that line to see what would happen if they were able to reduce something that low. So if this is the temperature, this is the volume. Since they actually couldn't get to 0 Kelvin, absolute zero, they could look on the line to see what might happen. Okay. And it turns out, if they were able to cool something to negative 273 degrees Celsius, the volume would actually go to zero. So the gas would have no volume whatsoever, which is really weird. And of course, getting something that cold in the 1800s would have been impossible. Um, but they could at least figure out this limit and think about the implications. So they know a gas with no volume would also have zero pressure and therefore no kinetic energy. So we could think about this in terms of if we started here in this diagram at 0 degrees Celsius, so right there at the freezing point of water, but we don't know if this is water, this is just a gas. Okay, so if we heated this like plus 100 degrees Celsius, well, that means we're going to increase the volume by 1 over 273 100 times. So we have the original volume plus, it's going to increase, right? So plus 100 over 273. Now, if we cooled it, so here you'll see we're going to take away, so minus 100 degrees Celsius. Well, that means we start with the original volume, because the original volume we're just saying is 1. If we start with the original volume and then we cool this thing, we're going to subtract 100 over 273 from the volume. So you can see it's actually going to be larger here, and it's going to be more compressed here. So the whole idea is, well, what happens if we keep cooling until we hit this, until we actually reduce it to the full ratio there, 273 over 273? Because this does equal 0, which means the volume is non-existent, no volume. And that's the whole idea behind absolute zero. It's just freezing something, a gas, so much, getting it so cold that it just goes away. There's no actual energy to lift this lid, this cylinder up. So when atoms and molecules lose all of that kinetic energy is pretty much that definition of absolute zero. They have no more energy to give out. Also, when you hit absolute zero, you can't lower that temperature anymore. So that's why there's actually no negative numbers on the Kelvin scale. As soon as you get down to 0, you can't get any colder than that. It's impossible. So that's why the Kelvin scale starts at 0, absolute 0, and goes up. And you can see that over here. So starting at absolute 0, you can see that helium and oxygen have some of the lowest boiling points out there. So pretty much, unless you're really close to absolute 0, you're always going to have helium or oxygen gas. As you start moving up, you can see where dry ice vaporizes. Dry ice is still very cold. Then above that, you start getting to the everyday things, like where water boils, where iron melts. You can get up here to the surface of the sun, which is 6,000 Kelvin. And it turns out you can actually get way hotter than the surface of the sun. The sun is not actually that hot. So you can actually go up here to the center of the sun, or you can go up and think about the heat inside of a fusion reactor, like a nuclear fusion reactor. And that's literally like 100 million Kelvin, which is insane to think about, that we can actually achieve temperatures that high on Earth. So this is going to lead us to the first law of thermodynamics. Um, So we have this absolute amount of heat, right? Anything above 0 Kelvin has some energy in it. Okay, now we can talk about the transfer of that energy. Uh, in a previous lecture, I talked about the idea of caloric and caloric heat, which is what they used to think heat was. They used to think that the like a caloric transfer was it was like a fluid or liquid heat. But we now know heat doesn't transfer by some weird caloric fluid. We know that it's a transfer between like molecular collisions. It's a transfer between the objects themselves. So today, heat is just viewed as a transfer of energy from one place to another through those molecular collisions. Um, and what we can do is we can actually take that first law of conservation of energy, or sorry, the law of conservation of energy, which is energy cannot be created or destroyed. So I'm just going to say E cannot be created or destroyed. Essentially, if we take the law of conservation of energy and just turn that into something that includes heat, we have the first law of thermodynamics. The whole idea here is essentially for the first law, when heat flows to or from a system, right? So either we're going in or out of a system, the system gains or loses an amount of energy. Gains, let's see. Let's do it this way. The system gains or loses an amount of energy equal to the amount of heat transferred. Okay, so this is going to be Q, because we were talking about the amount of heat in something is Q. So essentially, what this is saying is if we have Q in, Q out, that's going to be the same as the amount of internal energy that the system gets. So we'll represent that as a U for like a potential or internal energy. So this is just pretty much accounting for this system that we're looking at. This can be any system. The first law of thermodynamics can be applied very broadly. But then the question remains, what do we mean by system exactly? We keep saying it's the flow of energy in and out of the system, but what does that mean? So a system means a well-defined group of atoms, molecules, particles, or objects. Okay, we get to pick the definition just as long as we make sure it's nice and strenuous and includes some sort of things that are going to be picking up or giving off energy. So what is contained within the system and what is outside the system must be defined. Okay, so what's inside and what's outside, those are two very important things. So adding heat to a system, when we do that, we'll do one or two of these things. So obviously, if we put heat into a system, it increases the internal energy if it remains in the system, right? So if we put heat in plus Q in, if it stays there and doesn't leave, right? So if this doesn't happen, it'll increase the internal energy of the system. So we're going to get a plus U of the system. Oops, I should say does work. Yep. So also, if we add heat, it does work on things external to the system, right? So if it actually leaves the system, then we're going to get some work done. So you can think about like an air parcel. If we add heat to it, it's going to expand and push other air out of the way. So one hot parcel of air, little clump of air, when it expands due to incoming heat, it's doing work on the rest of the atmosphere around it. So it's pushing all of that out of the way. So in equation form, the first law essentially states heat is added to the system plus Q, and that heat in turn will be either an increase in internal energy. So we're going to get a plus delta U, because that'll be like a temperature increase, something like that. Or if that system starts doing work on its environment, okay, the heat that we add goes to the increase in temperature, and it could be assigned to the work done by, in this example, the air parcel, right? So this is work done by the system, and anything that the system does, we always represent as positive work. If we do work on the system, maybe if we come in with our magic hands and we collapse this air parcel that's trying to expand, if we make it smaller, well, then that's going to be negative work because we did that to the system. Again, this first law of thermodynamics is simply the thermal version of the law of conservation of energy. The first law is an overall principle that is not concerned with the inner workings of the system itself. So that is important to note. So it doesn't matter if we're looking at like a car engine or something like that. Maybe we're heating a beaker of water. The system itself, the thing we're looking at, doesn't matter. It's just the transfer of energy that we're worried about with this first law of thermodynamics. So the details of the molecular behavior, whatever's going on, doesn't matter. That means that essentially thermodynamics is just describing the macroscopic, everyday things, bulk properties you can see. We're describing those macroscopic movements of heat. So actually, when thermodynamics was just starting as a field, they didn't really even know about how atoms or how they worked. So that's why thermodynamics focuses on these bulk properties of matter. Ooh, that's terrible. Let me erase that and try again. So this is the focus on bulk properties. So we can explain the thermodynamics and what's happening at the molecular level, but mathematically and using the models of thermodynamics, it's just the overall big picture of a system, what's happening. All right, so let's consider the paddle wheel experiment, which is actually a pretty cool thing. So essentially in this experiment, when the weights drop, they're essentially going to turn this pulley, and that's going to cause the paddle wheel inside to turn. So essentially the gravitational potential energy of these masses, so we have gravitational potential energy, that gets turned into heat to go inside the water. So you'll see when you drop these two masses, we get plus Q, so the temperature rises. So we actually convert mechanical energy from gravitational potential energy into heat Q, which is going to increase. You'll notice that we actually didn't put any heat ourselves. Like we're not heating this with a fire ourselves, right? So no Q added. We're not holding a match under this. The only thing we are adding is work. We're only doing mechanical work with these two masses. So that means if we take our lovely equation here, the statement of the first law, Q equals delta U plus W, if we take that statement, we mark out everything that goes away, in this case, Q0, because we're not holding a match under this thing, okay? And then we know that if our system is the water inside, that's our system, the water's not doing work on the outside. The outside, the weights, are doing work on the water, okay? So the system's not doing work. The system is getting worked on, so to speak. So anytime when that work goes backwards into the system, that becomes negative. Okay. So that means we have this 0 equals delta U minus the work. Now we can simply just add the W over to the other side, and we get this statement. So since we don't have a match to heat up the water, what this is saying is that the work done by the masses, the weights, equals that change in internal energy. So the temperature rises. Okay. So all that temperature increase just comes from mechanical energy. And we actually have a name for this type of interaction. It's called an adiabatic process. And basically what this means is if you're going to compress or expand a fluid, because when that fluid heats up inside the container, it's going to expand a bit. When you do this, when you compress or expand a fluid while no heat enters or leaves the system, just like we showed, we did not light a match under it. It was in a big container, heat was not leaving. This is an adiabatic process. So when delta Q, there's no change, 0 joules of heat's exchanged, but you're still doing work on the system and changing the internal energy, that's adiabatic. So such conditions can be achieved by thermally insulating the system, just like we had on the previous slide, or performing a process so quickly that heat has no time to enter or leave. So we're thinking a very quick process, like we'll talk about in just a second, but essentially there's no change in that delta Q. There's no change in heat, that's 0 joules. And that leaves us with this simplified first law of thermodynamics. You can actually see this in everyday life when you use a pump, a bicycle pump, to pump up a tire on the bicycle, just like shown here. So you're not holding a match under the pump, but it still gets hot, right? So there's no fire making this pump hot, but because of the mechanical work and compressing all of that air inside, the mechanical work from the pump is actually converted into that temperature increase. And that's why if you pump up a bicycle tire that's maybe really flat, that pump will actually start feeling warm. It's actually from the compression of the air without heating it up with a flame or something. The second law of thermodynamics, since that was the first, the second law on the surface seems very straightforward. It just says that the heat, when it's left to do its own thing naturally, never flows from a cold object to a hot object. Heat flows, as we know, from hot to cold. That is the layman's term explanation of the second law of thermodynamics. If you want to dig deeper, you can look up something called entropy. And the whole idea of entropy is essentially a system wants to go from ordered to disordered. Just like a desk, you set at the beginning of the day, you put everything out on your desk, it's nice and organized. At least in my case, by the end of the day, my desk is an absolute wreck. And that is entropy. That's the whole idea of hot, ordered, high energy particles moving to low entropy or increasing entropy, right? More disorder. Those high energy particles want to go spread out just like warm butter on a pancake. That's the whole idea of entropy is it wants to move from this high area of energy to something lower where everything's more uniform. We see that in everyday life as heat moving from hot to cold, but there's a whole lot under the second law of thermodynamics that we just don't have time to talk about. But I do encourage you to watch some videos on entropy. It makes you very sad because you can relate entropy to something called the heat death of the universe. Which is a very sad topic when you talk about it in thermodynamics, if you're a physics major. Um, But that being said, the good news is heat can be made to flow the opposite way. So we could go from cold to hot if we wanted to. We do it all the time anyways. Um, the thing is, to make this happen, it's essentially an unnatural process. And all we have to do is we have to help it along by actually adding work. So this won't happen naturally for us, but if we put in a little work ourselves, we can actually make it. We can force this heat transition to work this way. So to reverse the flow, external energy must be added to the system. And this happens every time you use a heat pump, air conditioner, or a refrigerator. You're literally fighting entropy going back the other way. Um, the whole idea here, if we wanted to sum it up, is essentially you can have anything with energy and it can do work if it's going to move to something colder. So even the internal energy of an iceberg can be used to do work if it's going to do work on cooler things. So I don't know of anything really much colder than an iceberg. So you may not find it useful, but if you find something even colder than an iceberg, that iceberg has enough potential energy there, thermal energy, to do work on it. All right. Um, Now that we have the first and second law discussed, we can actually talk about heat engines, because they actually use the first and second law here, because we have energy flowing from hot to cold, we have work being done. So heat engines are sort of going to wrap up the ideas of the laws of thermodynamics here. So a heat engine is any device that operates from a difference in temperature, okay? So anytime you have a difference in temperature, you can actually get work out of that. We know that now. And any instrument, any device that uses that temperature gradient from hot to cold, that's essentially a heat engine. The thing with heat engines, though, and this is true for all of them, only some of the heat can be transferred into work. Okay. Um, you're going to lose some heat in the process. You can't have this temperature gradient and you can't get all the potential energy out of that to do work. You're going to lose some. That's just a fact of nature. But the whole premise here is essentially because heat flows from a high temperature reservoir and into a low temperature sink. This is our hot to cold. This is what we're going to harness. And as that temperature flows, as you can see in this picture, as we go from hot to cold, we know this is going to happen, right? We know we're going to get this hot to cold. Hold on. Here we go. We know we're going to get this hot to cold flow of energy, but what this heat engine device will do is it's going to steal some of that transfer and actually use it to do work. You can't steal all of it. Sorry. Figure out how to do that and you can become rich and famous. But essentially, this is a diagram for pretty much how every heat engine works ever. So with every heat engine, it's going to gain heat from a high temperature reservoir. Okay, and that's going to increase the engine's internal energy. So we're getting a big plus U, and that just comes from T hot. So this could be from like burning gasoline in your car's engine, or using a nuclear reactor to generate steam, right? That's really hot. And you can use that steam to power homes and businesses in a neighborhood. It doesn't matter how the engine gets that energy as long as it comes from something hot. And you can do whatever you want to make a hot reservoir. As long as you get it hot enough, you can have an energy, you can have an increase in internal energy in the engine. Okay. Now, as I said, some of this internal energy can be converted to mechanical work, but not all, okay? The rest actually gets kicked out, and the heat you would like to have to do work gets kicked out to the low temperature sink. And just like a kitchen sink, stuff goes in, doesn't come out, essentially. So this is a cold sink. And you're always going to lose some of that heat energy from the engine to a cold sink somewhere. If it's on your car, it's the exhaust from the tailpipe. That's your cold sink. It's just the atmosphere outside the car. What we can do is we can actually rewrite the second law of thermodynamics and sort of rewrite it to say things specific about heat engines. So again, the basic layman's version of the second law of thermodynamics is heat flows from hot to cold. Okay, well, if we write this in terms of a heat engine, we can say work done by a heat engine only takes some input heat, and converts it to work. The rest flows or is expelled as T cold, or is expelled to the sink, the thermal sink. Sometimes you might want exhaust heat if you're trying to heat up something like a cold room. Well, that exhausted heat is a good thing. But like with your car, if you could keep your car's exhaust from getting hot, you would have a more efficient engine. It would be essentially using more of that heat to go into the engine. So when this expelled heat is not a good thing, that's essentially just called thermal pollution. Yeah, right? So pollution's bad, even if it's thermal pollution. Anytime you don't want that, it just gets the label pollution. We can actually determine the efficiency of these engines, and this works pretty much. It's the idea that works on all engines, heat engines, that is. So in 1824, the French engineer Carnot, sounds like Carnot because he's French, and French has really weird pronunciation. So Carnot actually discovered that the greatest fraction of energy that's being inputted, he figured out how to calculate from that previous diagram. He determined how to calculate the sort of best possible scenario to essentially get the ideal efficiency of an engine. And what that depends on is the difference between the hot reservoir and the cold sink. So if you know what these two temperatures are, the hot reservoir and the cold sink, you can actually calculate the best possible scenario for any engine. If you use this equation, this is important, but if you use this equation, since this is a ratio of temperatures, then you need to use the Kelvin scale. Anytime you have temperature over temperature, you need to use the Kelvin scale, because you can imagine what if we were working with something very cold, like maybe our cold sink was minus 100 Celsius, and then our hot temperature was 0 Celsius. You can't plug 0 degrees Celsius into this equation because it's a division by 0. That's why you have to use the Kelvin scale, right? Because nothing can ever really get to 0 Kelvin, or at least we've never been able to get something to 0 degrees or to 0 Kelvin. So you never have to worry about a 0 in the denominator here. So that's why you need to always use the Kelvin scale for calculations like this. But again, when you do this calculation, remember, this is for the best case scenario. This equation doesn't account in like things like friction and drag on like moving parts of an engine. So the true efficiency of any engine will always be less than what you calculate. It's just this will give you the best possible scenario. So let's take this equation and actually look at two very extreme examples. So first, what would be the ideal efficiency of an engine if its hot reservoir and exhaust were the same temperature? So what would happen if T hot and T cold were the same? Okay, that's the first question. Second question is, what would be the ideal efficiency of a machine that has a hot reservoir at 400 degrees Kelvin, sorry, 400 Kelvin, because Kelvin doesn't have degrees, okay? The hot reservoir is 400 degrees Kelvin, and a cold reservoir is at absolute zero, so 0 Kelvin. Okay, so let's think about what would happen with these two. In the first case, when the reservoirs are the same temperature, well, that's just going to be 400 Kelvin minus 400 Kelvin. That's going to give you 0 in your numerator. So the ideal efficiency is actually 0. That means essentially you get no work, nothing is happening. Which makes sense because if a heat engine works off of a difference in temperature, if you have no difference in temperature, you don't get anything out of it. It's not even a heat engine anymore because it has nothing to work with. There's no temperature gradient. On the flip side, okay, if we look at the situation where T hot is still 400 Kelvin, but T cold is absolute 0, well, if you simplify this, it turns into 1. So this is absolute maximum efficiency. Write that better. Oh, because I can't. So the whole point of this right here with the maximum efficiency is that the way to get the best possible scenario out of any engine, like your car engine or whatever, drive in absolute 0. I mean, it's impossible, but that would actually make your engine 100% efficient. So that's your theoretical max for any engine will occur if it's running in the coldest physically possible scenario. Otherwise, you're sort of limited to your everyday temperature values. But these are the two extremes. You have when their temperature reservoirs are the same, you get nothing out of a heat engine. And if that heat engine sets somewhere in absolute 0, you get the best case scenario out of that heat engine. Everyday temperatures, other than that, you're sort of stuck in between here. So here's your everyday life. Stuck in between these two extremes. All right. That's got everything taken care of for the first two laws of thermodynamics, but this wouldn't be a true physics course if we didn't talk about, at least very briefly, how a piston-driven engine works. So this is essentially, if you drive a gasoline or diesel-powered car, this is more or less how they're going to work. There's one less step in here if your car is a diesel car. But otherwise, for a gasoline engine, all of this is pretty much the same. So let's walk through these steps. So we have a fuel-air mixture that fills the cylinder of a piston. Okay, so you can see here we've got some fuel-air mixture coming in. So what happens is, while this is happening, as soon as this gets sealed again, right? As soon as that gets sealed, the piston's going to move up and it's going to compress the gas, right? So you have all this gas in here, it gets squished. Now, this is just work being done on the system. We don't have a match yet. There's no fire. This is just the work being done, increasing the temperature. Okay, so we have an increase in temperature. This is work being done on the system. So this is an adiabatic process. So we can write it like this. Now, as soon as this piston gets to the top, that's when the spark plug is going to fire, right? So there is where your fire comes from, okay? So we have this instant flash of Q, so plus Q, but it's just a spark, right? Hence the name spark plug. So this is actually very short. It's not like a fire, it's just a quick spark. And what that does is it ignites the mixture, and that's going to raise the temperature. So it's going to have a lot of internal energy here. Now, in step D, since it has all this extra energy, it wants to expand. It's high temperature, it's trying to expand. Now, there's no fire anymore. So this is, again, adiabatic expansion. We're just looking at work and internal energy, right? So this is another adiabatic expansion. Now the question is, how might this be different than part B? So we still have work being done this way, but what's the difference between B and D? So in B, the engine, the mechanical part of the engine does work onto our system of particles. So since we have to do work to it, that's negative work. But now in part D, since these particles, they're the ones doing the work, they're exploding and expanding, that's going to be positive work. Okay. Now, once we get that explosion, you'll notice that this explosion is what's driving this part of the piston in a circle. And essentially what you want is you want this crankshaft to keep turning, right? So these pistons are what's going to drive that rotational motion, which you can use to then drive the car. Once that explosion and expansion happens, going back up again here, since this has exploded once, there's nothing left in there to burn, right? You burnt through all the fuel. The rest of this is just crap. And you want to get that out of your piston, out of your cylinder. So then it's pushed out and expelled essentially to the T cold. T cold. Here we go. And this is your exhaust. Okay. Now, if you drive like a 4-cylinder car or a 6-cylinder car, then you're just going to have 4 of these working together. Or if you drive a 6-cylinder, you're going to have 6 of these working together. Or God forbid you drive an 8-cylinder car because then you'd have terrible gas mileage. But this is the whole idea essentially behind how your car's engine works and why the number of pistons and knowing about the number of pistons tells you information about your gas mileage, the power that your car has available, because 6 of these pistons firing, like in a 6-cylinder car, is going to give you more horsepower than a 4-cylinder engine. And all that's going on in there is this cycle that includes pretty much the first and second law of thermodynamics. You've got your adiabatic expansions. You've got your temperature being, or your heat being put into the system, leaving the system. You've got work being done. It's all there. So you're essentially driving around with the laws of thermodynamics. All right. That being said, if you have any questions, feel free to email me and ask. Otherwise, this has pretty much finished the section on thermodynamics. So next time, we're going to move on to a different topic.